Before we start, a few words of respect for the Ukrainians who are still fighting for their freedom and for our freedom. Okay, today and next week, I'm going to talk to you about this system design approach. And there's some very interesting concepts. It's a mixture of system design and mathematical ideas. And it's very conceptual and very powerful. I'm going to start with some case studies. So the industrial one, there's many more, but because we only have 2 lectures, I only gave 2. And then I'll talk about, today, compositional systems. When you put blocks together, well, I make a client server. The client talks to the server. These are components. The server has a database, okay? And there's a network. It's all components connected together. And we will study them using 2 concepts called quality attenuation, which is basically a kind of delay, simple, and outcome diagrams, which are showing how the system behaves. Okay, I'll show many, many examples. And then next week we'll talk about systems with dependencies and overload and so on. Okay, so let me give an introduction. So I want to show you how to build big systems. Okay, big systems. So this is the target, with many independent users, like telephones or web commerce, Amazon, and real-time performance is important. Okay, you want the system to behave. I want to make a phone call. The connection should be good. So large flows of independent data, and there's overload. Very important. You design the system so that it behaves well when there's an overload. Okay, overload tends to be ignored. But for ΔQSD, it's very specific. We talk about overload. So here's some examples. Cryptocurrency. So one of the examples is, I'm going to give you, comes from cryptocurrency. Communications networks, telephony, whatever, mobile telephony, client servers, Amazon, big databases. Also, distributed sensor networks, when there's lots of sensors gathering data. So these big systems with lots of data flowing around. Okay? So this is a very important case. Many systems are like this. And this approach was pioneered by a company called PNSol, Predictable Network Solutions. Excuse me. Please. It was founded 20 years ago, and it was originally from the University of Bristol. And they have been working with many big companies. So British Telecom, Vodafone, and also in the United States, Boeing Space and Defence, something called Future Combat Systems in the United States Defense, IOHK, which is a company doing cryptocurrency. So they have the ADA cryptocurrency. I don't know if you have bought any ADA crypto coins. So these are the guys who do that. Okay? And they have done lots of studies, scalability, graceful degradation. So the main ideas comes from these guys. Okay, so what is it all about? So the idea is you want to design a system. I want to build a telecommunications system, a huge system with thousands or millions of users. Okay, so I want to know the performance before I build it. Okay, I want to predict. And feasibility means maybe I'm doing something impossible. I want to make telephone with low latency, 50 milliseconds. Maybe that's not possible with the technology. So I want to know very quickly whether it's feasible. Because if I start building and it doesn't work, I waste a huge amount of money and time. Okay. So ΔQSD lets you do that. So it's very powerful. And a few ideas, so it's compositional, so they put blocks together. It's stochastic, so we're going to talk about probability distributions. And we're going to talk about predicting performance, feasibility, also dependencies. So it really works for realistic systems when you have overload situations. Okay? So these 2 lectures, I'm going to give you the basic principles. So you will learn about there's actually 2 main concepts, and everything turns around them. One is called, it's a general term called quality attenuation. It means that when a system does something, the quality always goes down, okay? When I send a message and a message comes out, it takes time, so there's a delay, the quality goes down, okay? So the instantaneous would be the best quality. So this is called ΔQ, and then there's a concept called outcome diagram. This is how we build big systems, where we connect pieces together, okay? And we're going to build systems as block with outcomes that are connected together, independent parts. Next week I'll talk about dependencies and also refinement. So we start with unknown system and we slowly put in the pieces we know. So we're refining, okay? We don't immediately know the whole system, we're designing it. Okay, so refinement means it's step by step, you know more and more. And any time in there, even if you don't know the whole system, you only know a small piece, you can already compute performance and feasibility, okay? Okay, so that's the basic ideas. Now there's two main concepts. So the talk lecture today, I will try to give you real good knowledge, intuition about these. There's quality attenuation and outcome diagram. So quality attenuation is a kind of delay. Message comes in, message comes out. It takes time. If the time is 0, then it's perfect, but it's never 0. It's always bigger than 0. But the latency, the delay, is not a number. It's a cumulative distribution function. So there's a probabilistic aspect. So there's a whole spread of possible delays with probabilities. And the failure is also part of that. Because the distribution function, maybe it doesn't go to 100%. Maybe there's some failure there. Okay, so failure is also part of that. And then there's outcome diagram. An outcome is anything the system does. If I kick the system and it hits me back, that's an outcome. The kick is 1 at the start, the hit is the end, and the result is I get hit, that's an outcome. I send a message to a component, it makes a reply. The send and the reply together is an outcome. It's what the system does. It's little pieces of behavior, okay, with start and end events. Each one has a delay, okay. I send a message, get a reply, there's a delay, and that delay is the ΔQ. And now when you build a big system, you're combining all these behaviors together, because usually a big system has lots of little bits of behavior connected. And so the outcome diagram is the whole thing. So it's a directed graph, but the outcomes have a causal connection. Remember we saw causality, so one outcome might be causally relating to another. Okay? And of course it can also define partially defined systems. We do a refinement. It means you don't need to know everything. Okay? Okay, so let's now start getting more concrete. Here is a system component. The blue boxes, the blue will always be like block diagram. So this is a piece of hardware or something. A message goes in, query, response comes out. Very simple, right? The delay between query and response, that's the ΔQ. But it's not a number. It's a distribution. Okay, so if you have, it's a cumulative distribution function. So you know what that is. It means that for every delay, you have the probability that the delay is less than or equal to d would be p, okay? So as the delay increases, it gets closer and closer to 1. So this is a spread. It's not a number. It's always very fluctuating, okay? And sometimes there's no response. So for this piece here, the limit here is less than 1. That means even if the delay is infinitely long, there's no response. That means this is a failure. Okay? So this function also shows failure. Okay? This is a cumulative distribution function of the delay, but it's technically, mathematically, not a real cumulative distribution function because it doesn't end in 1. It can be less than 1. It's what's usually called an improper random variable, because the ΔQ is going to be fluctuating, but it's improper because the there is some probability that the delay is infinite. Okay, so it's a delay, okay? It's just kind of a delay. And now we build systems by connecting blocks together. So a very simple example, 2 blocks. The simplest example. I have a front end and a database. I do a user message. The front end sends a query to the database and there's a response. So I have 2 outcomes. This front end receives a mouse click or something. I type something and it sends a message. So those are 2 events. So that's one outcome. And there's a causal connection. This outcome will lead to another outcome. So there's a query going to the database, response coming back. That's the second outcome. So this is the outcome diagram. I'm always going to show it in orange, like this. So they're a causal. So this is a causal directed graph. Okay. So the total. What is the total delay from U1 to R1? It's the sum of the 2 delays. Okay. But these 2 delays are fluctuating. They're distribution functions. How do you add up to distribution functions? Well, you can add them up. And I'll show you how it works. But the total system delay will be the sum of these 2 delays. And the total system delay is also a distribution function. And this distribution function is what's called the convolution of the 2. Okay, so convolution is a way of adding things that are not numbers, but functions. Okay? So that's just intuition. But now let's go first to a case study. I'm going to show you a case study of many components connected together. And each one of them has a delta Q, has a delay. And then the whole system has a delay. So it's a big telecommunication system. But sometimes there's a problem. The delta QS, it's shown very bad behavior. So we have to do some kind of a reasoning, like Sherlock Holmes. We have to find the reason, diagnostics. It could be debugging, or we have to find why it's so bad. And so we're going to use delta Q to help us. Okay, so let me show you the first case study now. So we're going to show 2 case studies. There's more, but there's no more time. So one of them is a very nice one called the small cells. And the other one is called Cardano Shelley. Both of these are actual industrial case studies, so I'll give a slightly simplified version. They are covered by NDA, so I cannot say everything, but I will say the most important things. So small cells is actually like a debugger, debugging a system that has a problem. And Cardano Shelley, it's the opposite. We actually want to design the system. We want to avoid the problems from the start. Okay, so you can use delta QSD in that case. Okay, so let me show you now how the small cells case study works. So this is a telecommunications system now, real system. And the main character in this story is an MNO. MNO means a mobile network operator. I will not tell you who it is, but it's some big company who is the one that did this. Okay? And they deployed what's called small cells. When you have mobile phones, you have cells, which are geographic areas that are connected, that are controlled by one tower. Okay? So a small cell is a low-powered cellular radio access nodes with a range from 10 meters to 3 kilometers. They're small cells. And then it goes to a backhaul and so on. So this was the system. I'll show you a diagram in a minute. So this system, it worked, but it did not scale. When they used more than a few hundred users, the telephone connections just degraded. The voice quality stopped, and cells were failing. It was actually crashing and so on. How can this happen? Only we have a certain scale. So this problem was studied by PNSol, and I will show you the outcome diagram for the whole system, and we measure the delta Q, these distribution functions, and we pinpoint the problem. Okay? So they successfully diagnosed the system, and they fixed, and it was fixed And the company was very, very happy. Okay? But still, PNSol is not rich. They were paid their consulting fees, but in fact, the work was worth much more than that. They saved this company, basically. Okay, so here's a diagram of the system. Here's a user on this side, talking, and here's the small cell with the radio waves, and there's different pieces. Now, the whole communication goes down to a central core, which is owned by the MNO. This is the big company. And then it goes back to the other guy. So when I talk, and then there's one guy who is the source and another guy who is the destination. So it goes all the way from A to E and then back to A. Now the point is that this whole thing is not owned by the MNO. It's owned by different companies. Okay? There's local to the user, there's a thing called the wholesale access network, which is owned by a company. Then there is what's called the national interconnect. This is a bigger network covering the whole country. And finally, there's the core, the MNO, its own central core of the network. Okay? So there's several companies involved here, and this MNO that has contracts with each of these companies, they have to provide a service. So it's like renting this whole thing. The MNO doesn't own everything, it owns only the center part. Okay? But the MNO is accountable, so the service is, MNO is service. But there's the radio access node supplier, there's the backhaul, which is called the backhaul, and this is the core. Okay? So they make contracts. All these connection points would have to give certain bandwidths and delays, and it would have to be satisfied. But it didn't work. Okay? The MNO believed the contracts were good. The service we delivered and contained a hazard. So hazard is a probability of something going wrong. So they believed it was a very small hazard. Okay? Okay, so this system was not scaling. When I am at A, I'm making a connection, so it goes all the way to E and it goes to the other user, which is also an A. So from A to E and back to A, that wouldn't scale. More than a few hundred users, and things started crashing. So what's going wrong? Okay, so PNSol, they got to work. They put a synthetic traffic generator at the A with an observer to the which collects the data, and it would send data to the reference point. The E is in the center. Okay, and they have internal observers too. Okay, so that's very important. So all these points here, they put observers. So they put little pieces of software. These are like little eyes. These green things are eyes looking down. So they observe. They have all these observers collecting data, how the thing is working. Okay? And this is called spatial discernment. They want to see what happens in different parts. So the outline diagram looks like this. It's actually quite simple. You have A is I am talking. It goes to B, B goes to C. There's a packet, sends a packet to C1, C2, D, E. And then it goes back to the other guy, D, C2, C1, D, A. Okay? And each of these two guys is an outcome. It's a behavior. I send a packet here, it's received there, and so on. So each of these little chunks has a delay. Okay? Quality attenuation. But the contracts are assigned, and all the delays are supposed to be satisfied. Okay? So what's going on? So just a point, E, so there's lots of observation points, but I mean, they didn't need hundreds of them, but there's like this number, so like 9 or so, or 10, let's see, 10, 11. So each added point really improves what you can see, what's called spatial fidelity. So even if you just have A to E and E to A, that's doing upstream and downstream. That already gives you something. Okay, so what did they get from all that? So now we're going to do some detective work, and I'll show you. So these graphs are not the real graphs. but they are looking similar to the real graphs, okay, because of lineating. Okay, so here we have the system is running, runtime seconds, and things are going on. All these synthetic observers are talking, making phone calls. And the delay of each packet is here. So each little circle is a delay. So you can see most of them are like here. Some of them are a little bit higher. Okay? This is the A to E to A delay. So the whole round trip, basically. Okay? So that's what you see. Okay? Yeah? Nothing special, right? Okay, well now let's split upstream from downstream. So this is the packets going from A to E. E is in the center, then back to A. So E to A. So you can see already a difference here. The upstream guys have a lot of variation. Look at this. There's like huge variation. The variability here is much higher than the downstream, which is much more constant. Right? Seems. So this maybe is a problem, right? Is it a problem? Okay, so how does the delta Q enter here? Well, each of these points has a delay. And there's a distribution. If I take a slice here, this will give me some delay distribution. Like there's it's very heavy down here and it gets less here. So there's some distribution. Okay? So there's an instantaneous delay every point here. Okay? And we're going to be pinpointing down until we get to a slice. Okay? So the first observation, the upstream has a lot of variability. And the downstream is almost constant. Oh, you might think, well, that's a problem, right? Actually, no, that's not the problem. The variability, this is not the problem at all. In fact, we'll see the problem is in the downstream. Okay, so let's zoom in a little bit more. Okay. Now we zoom more, and we let the system run longer. Okay, and we scale it more. We have more users. So these are upstream and downstream graphs. But now I'm looking only BCD. B to C to D. And the other one is DCB. So if you look at the original diagram here, BCD is this part, right? It's the middle. BCD and DCB. We're looking at this part. We don't care about the edges. Because we notice there's something going on here. Okay. Delay. The delays. You can see that every once in a while there's like a peak. But these peaks are not so high. But here, there's something weird going on. There's a huge, enormous peak here. But you might think, well, okay, it's just one peak. Who cares? But so the delta Q here is very, very large, okay? So it's not stationary, it's not the same at every point, huh? It's changing all the time with these peaks, huh? But here you get a very large peak. And what we observe is that shortly after this, the small cell that wants to receive this fails, so it crashes. This is an anomaly. So now we zoom in. You want to zoom in on it. Okay? Okay? So it's actually, so this is the DCB. Okay? So let's look at DC and CB. Let's split them. We have DC and CB. So it seems DC is fine. The problem is in the CB. Okay? From C to D. Here it is. So we're starting already to zoom down on the problem. It's right here, the problem. We now need to really zoom in on it. So now we zoom in. Notice the horizontal axis. Now instead of going hundreds of seconds, we have second per second. 590, 591, 592. So here something happens at 595. So this is a strange kind of behavior. It's a huge peak. So we will see this is a typical behavior of a queue overload. All these components in the telecom, they have buffers, right? If I receive messages, I put them in a buffer because sometimes they come too quickly. And you might think that's a good idea, but it can be very bad because this you see what happens here. The buffer here is filling up very fast. So a burst of messages comes. It fills up very fast. Okay? But emptying the buffer is very slow. Because the buffer is empty, can be emptied very fast, but it's only it can be filled very fast, but it's only emptied at the rate at which the component can service the packets. That means this side is very long. It's much longer. It's actually almost a whole second when basically nothing happens. Okay? So you can get into trouble, fill the buffer very quickly, get out of it much more slowly. Temporary overload has a very long-lasting effect. And we will see that when we study what the delta Q is for a Q component. Okay? So the problem is due to Qs and buffering. So here, this is a problem, okay? So is this really the problem? Well, then the PNSol guys made a formal model using outcome diagram of the whole system, and they compared the calculated behavior of the model with the measured behavior, and you can see that the model is doing pretty well here, right? It's not exact, it's following the structure. So if you feed it with the packets at the times that they're coming in, the model, the calculated behavior of the model will be close to the measured behavior. So that gives them confidence that the model is reflecting reality. Okay? This is really the problem. Okay, so now we can make a diagnosis of this. And the problem is in the whole cell access network. So if you look at the original diagram, it's from C to B. Okay? So it's here. Go downstream. So things are coming here, but they're stopped. Okay? They don't go on here. And the small cells, they need these packets because they have control loops. And if they have no packets for a long time, they will fail. Okay? Okay. The arrival rate from the MNO side exceeds the service capacity of the down side, which is XDSL line. So there's temporary overloading. But the temporary overloading lasts a long time. Okay? It degrades behavior for a long time. Okay, good. But this is not what the contract says. The contract says that the delay is bounded. Well, here we're breaching the contract. How is it possible? The bandwidth is good. The bandwidth of the receiver is higher than the bandwidth of the sender, but still the contract is being breached. Okay? And all traffic is being delayed, including the control traffic for the small cells. And they fail if the control loops are too slow. So this is 5 times maximum. So the small cells are basically crashing. It's like they see nothing is happening, so they don't like it. The control doesn't work. Okay? So the voice quality is affected. You have interruptions in voice. When the users notice it, it's very bad. Huh? So small cells, they breathe, means they stop. They stop for a while, okay? So this really makes the system very bad, okay? Okay, so this is what's called an unmanaged hazard, and the subsystems don't compose. So when you connect 2 components together, the receiving component has to fit with the other one, and they compose. But here they don't. The problem is the contracts were matching bandwidths. The bandwidth here is less than the bandwidth here. We're good, right? No. They actually didn't take into account the fluctuations. So you have to actually match delta Qs, and not bandwidths. So then so this is kind of a funny thing. So MNO, the PNSol then said this equipment here, you have to replace it by this kind of better. So they had to basically upgrade part of the system. And then every big company has what's called a corporate risk register. It's like a memory, keeping track of what happens and what are the fixes. And they said, we recommend you do technical training of your people And they tell me that the company did not really follow those recommendations. Okay, so that's the small cells example. And there's another example. This one is now, it's quite a different one. The previous one, the small cells example, was debugging, diagnosis, okay? The system was already running, we need to fix it. Here we actually design the system, it doesn't exist yet. So prevention is better than cure, for disease as for system. So PNSol designed what's called the Cardano Shelley, which is part of a blockchain. So blockchain is a part of the cryptocurrency, and it supports a cryptocurrency called ADA, developed by a company called IOHK. So this is one of the major, I don't know what status it is, maybe it's number 5 or something. It's a big cryptocurrency. And part of it is called block diffusion. And so you know that the blocks come together in a blockchain. So blocks have to be distributed to between nodes. So there's an algorithm called block diffusion. And the initial implementation was not good, it was too slow. So they did a new implementation called Shelley, and they designed it using ΔQSD to make sure the delta Qs were good from early on. Okay? And this one actually worked. And I will show it to you later when we start talking about outcome diagrams. So I'll give you more detail of this example later when we have the information. Okay. Okay, now let's start building systems. Okay? I start with compositional systems. So when you build a system, big system, you do it in 2 steps. First is you assume all the components are independent and you connect them together. And then you notice there's actually dependencies. Maybe these 2 guys are using the same power supply or something, or they're sharing a network. So you have to add the dependencies. So we'll do that later. But most of the pieces are actually independent, okay, in most systems. And so that's what I will do now. Well, the dependencies we'll do later. I will talk first about quality attenuation and then give you some examples with outcome diagrams. Okay, so let's say a little bit about quality attenuation. So, as we saw before, we have a component with a message coming in and out, and we have a cumulative distribution function, and there's a delay, okay? And there's also a chance of failure. The message might be dropped. And the delay is not always the same. And this is modeled by this probability distribution. It's what's called jitter. The delay between 2 successive packets will be different. So the packets are kind of vibrating with respect to each other. So this is called jitter. P% of messages have delay less than or equal to D, and F% of messages fail. So these are the 3 pieces that we're looking at. So the actual delay and the failure are both part of this. Okay, so that's what we saw. Let me just say a little bit about that. Delay and failure, we combine them. Usually people look at delay and failure separately. I send something, it's delayed, but if the component fails, that's something different. Well, in this approach, they're combined. Because there's actually connections, as we will see, between delay and failure. And there's trade-offs. You can actually reduce failure by increasing delay. For example, changing the delay threshold. Maybe you just say the system is tolerating more delay. So that's kind of an artificial way of reducing failure. Or maybe you retry. Retrying will increase delay, of course, but it will reduce failure. Okay, so they're actually deeply connected. Okay. And just a few things now about delta Q. You can actually compare them. Remember, causality was partial order. This also was partial order. You can't always compare. So this delta Q, number 1, is less than delta Q2. The delay is less because it's always less. But in real life, it might intersect. And if they intersect, then there's no order. Okay? So it's not always possible to compare. That's important to know. And I also want to say how delta Qs are added together. So this is a refresher, hopefully, for many of you from your days when you did some kind of probability. So here we have two components with two delta Qs. So here are the two distribution functions. Okay? So this one has a longer delay than this one. Now the total thing has some delay. What is it? What is delta Q of the whole thing from M1 to M3? So this thing is some function of those two. But of course it's going to be slower than these two. But what exactly will this function be? That's a very interesting question. And let me just give you a little bit. So you have probably seen already the notion of convolution, right? So you know you have a very strong intuition of what it is, convolution. Well, I will give you some intuition now. So if you didn't understand it before, you will understand it now. So here is the, I'm not going to look at the cumulative, but I'm going to look at the probability density function. So that's the derivative. And when it's very high, the density is very high. That means there's a high probability of something happening there. When it's low probability, okay? And so the probability, the delay between two numbers is just integral, huh? It's just this integral, huh? So this is just a derivative of the cumulative one, huh? So the area under this curve will be equal to 1. Huh? Okay, so we have the density of A and of B. So A has this maximum density dA, B has a maximum of dB. And this is the one we want to compute, the final one, AB. So the question, how likely is a total delay T? Well, when do we get the total delay T? Well, we get it when we have some delay in A and some delay in B, and the sum of those two is T. Okay? So we have some delta and then some T minus delta. So the sum of those two is T. So how often does that happen? So there's a delta plus T minus delta. How often do we get that with a particular value of delta? Well, the probability density of that is the product of the two. Why is the product? Because they're independent. Okay? Two independent. The two components are independent. And so, in order to get the total probability density, we have to make the sum over all deltas, for all possible values of little delta. And since we're looking at infinitesimals here, it's actually an integral. Okay? So it's the integral from 0 to t of the first PDF of delta, the second one of t minus delta. So this tells you what convolution means. Convolution means is that when I go from here to there, there's many paths, many ways to get there. And the convolution basically adds up all the different paths. Okay? So adding the two is just a convolution. Okay, so that's important to know because convolution is an important thing we need to do in ΔQSD. Okay, now let's start doing some system design. First, I'll just use delta Q. We can use delta Q to help design a system. So let's design a system with two components. Ta-da, just two components, okay? Like this. And the system needs to have some kind of a behavior. So we have to put these together and it has to have some total behavior. Very simple example, huh? And I'll show you top down and bottom up. We basically want to determine the behavior of the whole system or of a new component. We can even say when it's impossible. If the design tells us that the delay has to be negative, then we know it's impossible. Okay? And so we'll use delta Q. But to make the example simple, I'm going to use a very simple distribution called a uniform distribution. This lets us do back of the envelope. In the lab session in 2 weeks, we're going to use a tool, but today we're going to do back of the envelope approximation. So here's a uniform distribution. So it's very easy, huh? Nothing happens. When we get to A, it uniformly goes up. So all the values between A and A plus SA are equally probable. And when it reaches 1, it's 1. Okay? And this is a nice, simple distribution. And it's basically approximating a component with a buffer and a server. So a real component will behave approximately like this. You notice that, okay? So this is a simple distribution, and it lets us do back of the envelope. So that's what I'm going to do today. We're going to have a lab session in 2 weeks. We're going to use a tool with a web interface in a Jupyter notebook. And this tool will calculate automatically any delta Q and will show a beautiful curve. Of course, the tool can do much more than back of the envelope. But for today, we're going to do back of the envelope. So here's our first design. So this is bottom-up design, so it's very simple. I have two known components, A and B, and they have known behaviors. Question, what is the resulting behavior? What is the overall delay? Well, it's the convolution of these two, okay? Delta QC is the convolution of A and B, but we can approximate that. With the uniform, you can actually approximate it. So basically, the minimum delays, C is the delay of this one, A and B are the delays of the others. So C is equal to A plus B, but a little bit more. Plus M over 4, where M is the minimum of the two spreads. So it's a little bit worse than just adding two delays. And the new spread, so this one, will also have some kind of a spread. It's the maximum of the two spreads, but a little bit worse, plus n over 2. So the factoring of a spread makes things a little bit worse. But let me give you a numeric example of this. So here's a system whose delay is between 5 and 10 milliseconds. And another one, also delay in 5 and 10 milliseconds. If I connect those two, what's going to be the result? It's not going to be between 10 and 20, okay? It's going to be worse than that. Okay, so the C, so little c, it's 5 plus 5, but a little bit more. So that we have to actually look at the minimum spread. It's the minimum spread that is making it a little bit worse. So this is an approximation, and I get it by doing the actual computation and then making an approximation. So that I have to add m over 4, which is 1.25. So instead of being 10, it's 11.25. So the overall delay is a little bit worse, okay? And the spread, instead of being the max of the two, so 5 plus 5, it's a little bit worse, okay? Instead of being the max, it's going to be, oh, I made a mistake here, sorry. It's the maximum, not the sum of the two, okay? But anyway, I have to add 2.5. So there's some number here. So the actual spread will be 5 plus 2.5. Oh, sorry, I made a bug. Oh, it's nasty. You only see it when you teach. Okay, so the actual spread is the max, which is 5 plus 2.5. So 7.5 instead of 5. Okay, because there's two independent spreads, it makes things a little bit wider. So it's going from 11.25 to 11.25 plus 7.5, which is 18.75. So it's going to be a little bit worse. Okay? So that's approximate. This is not exact. Back of the envelope. Huh? So you see, this is kind of nice when you're designing systems on an envelope. Huh? If you want to use an envelope. Well, let me give you now another way of designing, actually, which is even more interesting. This is the top-down design. So now I have the same diagram here, but now I know the overall delay. I know it. So it's basically a requirement. I know what delta QC has to be, and I know delta QB. I already bought this component, and I know what the overall one. And my question is, what is the requirement on A? How slow can A be so that A and B together will still satisfy that requirement? Interesting question, huh? How slow can it be? And it's important to know that, because if we need a very fast A, it's going to cost money. And if maybe the delay here is negative, then we know we cannot satisfy. Okay? Okay, so let's do it now. So we use the same formula as before, but now we compute A. So this is back of the envelope. So we have C is A plus B plus M over 4. So what is A in terms of B and C? So A is C minus B minus M over 4. But it's allowed to be less than or equal to that. So C minus B, the difference between the two, but it's actually should be a little better than that. It has to be in M over 4. Okay? So A is actually strictly less than C minus B. Now the SA, the spread, is harder because the spreads are computed using this maximum and minimum. But we can make an assumption. But let me show you a numeric example and you see what's going on here. Okay? So here's my numeric example, if I can get to it. So we know the overall performance has to be between 7.5 and 15 milliseconds. We know B is between 5 and 10. So what constraint does that impose on A? Interesting question, huh? So we have these numbers. B, 5, 7.5, 5, 7.5. Now we make an assumption. Let's assume that the spread for A will be similar to the spread of B. That makes the calculation either. That's the assumption we can make. The minimum will be 5. What is the delay then of A? Well, it has to be C minus B minus M over 4. 1.25 milliseconds. Oh, that's very nasty. It's very small, huh? So 7.5 minus 5 is 2.5, but actually this one has to be even better than that. Luckily, it's greater than 0, huh? If we assume, for example, that there are other constraints on the spread of A, if this number becomes negative, it means it's impossible. Okay? So SA is the same as B, so it goes from 1.25 to 6.25. So this would be a possibility. You see that A has to be pretty good, huh? Because B is actually not that good, huh? B is already giving 5 milliseconds, and C is 7.5. So B is actually a pretty bad guy, not very good quality, and that imposes a strong constraint on A. Huh? A has to be pretty good. Huh? You see how that works? Nice approach. Huh? So when you build systems, this kind of calculation is very good to do it. And this is only back of the envelope, but in real life, you use a tool and it actually computes precisely, and then you get more precise answer. But this already gives you an idea. So top-down design is very interesting. Huh? It's actually doing the opposite of convolution. That's another operation called deconvolution, which is actually much harder to do than convolution. But if you make some assumptions, you can do it. Like if you assume the distribution is uniform. Also, a tool can do it. It takes a lot of computation, but for a laptop, today's laptop, it's not a big deal. Okay? 50 years ago, deconvolution was a very big deal, but today it's not a big deal. Huh? It can do it. And there's another point I want to make between difference between bottom-up and top-down. So bottom-up is very straightforward. You compute the known behavior of a component. And if the delay decreases, then it's better. But top-down is actually computing a requirement. It's saying the worst possible that component can be. So if the delay is less, that actually is harder. It's actually harder to satisfy it, okay? With the delay it's less. So top-down is actually computing with requirements, okay? Okay, so that's designing. Interesting, huh? You can also do diagnose. This is the small cell example again, but now I show it formally. I have a pipeline of components, and the overall delta Q is bad for some reason. And you can actually do a kind of binary search to find out why it's bad. Okay? So this is kind of the small cells example in this approach. Huh? Okay, so that was very simple, huh? But connecting components is not the end of the world. There's many more interesting systems. Let's now look at more bigger systems, more better ones. Okay, so let's design big real systems now. So you can't just connect two. You have many, many pieces together. So somehow we need to describe these big systems. And that's why we invent this idea of outcome diagrams, where all the pieces are there. We combine all these little outcomes to get big outcomes. So outcomes are behaviors, basically, yeah? Little pieces of the behavior, and combining them to get a big behavior. Okay? So this is a way of defining systems. It's actually, what do you know about defining systems? You've heard about UML diagrams, right? Well, this is very different from UML diagrams, because UML diagrams talks about the internals of the system, the classes, the states, the state diagrams, etc. But the outcome diagrams doesn't say anything about the internals, how we build the system. It's only looking at the system from the outside. I'm looking at, I do something and something happens. I don't care how it's done. It's purely observational. So it's actually a very different way of looking at system than a UML diagram. Also, it's a very useful thing, as we will see, because you can make outcome diagrams even when you know almost nothing. You can just do a very partial one. And you can bring many things together. Electronics, mechanics, humans, natural phenomena, anything can be an outcome diagram. Because we only worry about the outcomes. We don't care about how it's done. Okay. So we go now slowly to what it is. And I'm going to show you some real nice outcome diagrams. Okay. So here's the basic idea. It looks almost the same, right? But actually very different. On the left I have an actual component, piece of hardware. Message comes in, message goes out. Okay, this is actual piece of hardware sitting there, it's running. Outcome diagram is something very abstract. It's a relationship, a causal relationship between this event and that event. All that O1 says is that R1 causally comes after Q1. It's just a causal connection, basically. So an outcome is just a causal connection between a start event and an end event, which could be anything the system does. Huh? So I flip the switch and the light comes on. So flipping the switch is a start event, the light coming on is an end event. And between the two, there's a causal relation and there's a delay. Okay? There's actually a delay, quality attenuation connected there. Right? Okay? So that's an outcome, but it looks still they still kind of look the same. Here also, I have two components now. A U and then a message coming out, and then it goes to, well, I have two components sending messages forward in the message pipeline. But in the outcome diagram, I have a causal connection. So O2 is causally happening after O1. Okay? So it's a causal connection. We need two things the system is doing. Okay, and the total delay is the convolution. So we saw that. Okay, fine. A little bit more precise. This diagram here, these outcomes are actually like classes. It means you can have many things going on. Each time I have a message coming in, I click and a query is sent. I do many times. Each time I get an instance of this outcome. Okay, so this diagram, it's more like classes. You can have many outcomes that are like this. Whenever a U and a Q are occurring, it gives me an O1. So new instances of O1 can occur when you have new instances of U and Q. So it's not like there's only one message in the system, okay? There's many messages U coming in, but each message U has a message Q that's causally after. Okay? So the outcome diagram doesn't just talk about single messages, it talks about flow of messages and it's obeying. Okay, so that's all the theory. Now let me show you some examples. So here's a little bit more complicated example. Okay, and then I'll show you many more complicated examples, but maybe I do a break and we'll show the examples. I'll show you a bunch of examples of different kinds of systems on the outcome diagrams. So here's an example which is still pretty simple. It's like a client server. So I'm sitting at the computer, I click on something in my browser, stuff happens, and eventually something is displayed. So there's many things happening when you do that. I click, internal to the browser, a query is created. This query is then sent on the network. The server receives that query, does some computation, sends a response, and the response is received again at the browser. And then the browser treats that response and computes what it has to display, and then it calls the display function to display something. So each of those pairs is an outcome. So I click, I create a query, that's an outcome, that's one outcome, it's a behavior. The query is sent on the network, eventually received, that's an outcome. So you have here 7 outcomes, and the total delay is basically the sum or the convolution of all 7 outcomes. Okay, so that's a simple kind of sequence, huh? Okay, now let me show you kind of first a general thing. I'm designing a system, and I'm designing it like this. I have some input event. The system does stuff, and it results in some output event. Okay? So I'm building a big data system, and I feed it something, and something's coming out. But this gray circle means I still don't know what's here. I might have a requirement of the delay, right? But I don't know this. So I do a refinement step. I say, well, I first send a request, and then somewhere somebody does something, and then it sends a reply. So I have these 2 pieces. Okay, so some of it is known, the rest is still unknown. And I can already compute delta Q's for this. Huh? And now let's say that this is database. So there's a database request and a database reply here, okay? So this is going into the database. The database receives it and sends a reply, and then I have a reply. So here I have my full system. So you see, step by step, I can design the system. Okay? So here's kind of an example. So this is top-down. Huh? This is like our top-down approach. Huh? So here we have a whole system, delta Q system. So we know how fast it has to be. We know how fast the request is, delta Q request. We know how fast the reply is, but we don't know this one. It's still unknown here. So we know delta Q system, delta Q request, delta Q, we know them. We can compute the conditions on the unknown, delta Q unknown. So what is the minimum delay of this guy that we still have not designed yet? You see, you can actually make requirements on the pieces you don't know yet. Okay? What happens if it's infeasible? So assuming delta Q unknown has to have negative delay. Well, that's not possible, not today. That means it's infeasible. That means it's impossible to build it. We have to go back. And something's wrong. Maybe the request is too slow, or the reply is too slow, or maybe the overall system requirement is not good. So if you have an infeasible system, you actually have to go back and redo something else. Okay? So if you want to look at full system design, it's like a tree. So little blue nodes are partial systems now. So we start here. We have a totally unknown system, the gray box. Each of the little d's is a design decision. So I add components, I refine it. I go down to 2, then at d4, then d5, d6, and now I have my system. So the leaves of this tree are the fully designed systems. And internal nodes are partially designed systems. Okay? So let's say I make a decision, d1, and then dx, and I'm here. I still have a partially designed system. But when I compute the delta Q unknown here, it's negative. That means it's infeasible. That means it's not, I don't have to go on. It means this whole triangle can be pruned away. That means anything coming later, once you get to something impossible, it's not worth going farther. So you can actually detect infeasibility very early on. You don't actually have to design the whole system, okay? You can compute infeasibility even for partially designed systems. If the required delay is negative. Okay, so that's very theoretical. Let me show you now some real concrete examples. So the first example is a cache memory. And now we go away from outcome diagrams so there's just sequences. Now I introduce operators. Now we have more sophisticated outcome diagrams. So here's a cache. So this is the cache, this is the block diagram. A cache and a main memory. I do a read request, and if it's in the cache, I get a hit and I go back immediately. If it's not in the cache, it's a miss and it goes on to main memory. And then it returns. Okay? So this is the memory, and in the refinement, this is now the cache. And now, you see, I introduced this operator here with this double-edged arrow. This operator is called probabilistic choice. So the cache, when we read, it has two possibilities, hit or miss. And probabilistically, there's a certain chance of hitting, let's say 95%, and 5% chance of missing. And the probabilistic choice models that. So it has two outputs. So this is a prefix operator. Right? We make it prefix because we immediately know what operator we're doing. It's not at the end. When we start, we already know this is a choice. So when it hits, we have this outcome, hit outcome. So the hit is an outcome. When it misses, we have this miss outcome, and then we do a main memory read. So we have another outcome, which is the main memory read. And we can compute delta Q for this whole thing. If we know the hit and the miss ratio, if we know how long it takes to do a hit, how long it takes to do a miss, and how long it takes to do main memory read. And in fact, a probabilistic choice is also a computation. You can compute the delta Q, and it's basically a weighted sum. We're actually adding the CDFs. And why does this work? I'll show you. This is actually symmetrically correct. The hit ratio times the delay of the hit, plus the miss ratio times the delay of this part. But this part is a miss followed by a main, so it's a convolution. So we can actually compute the overall cache behavior from the behavior of the components. And here's a diagram of it. So let's say the hit takes 1 unit of time, 1 nanosecond. 95%, it goes like this. Immediately, step up. The miss is a little bit slower. It doesn't matter because it's only 5% of the time, because the system is optimized for hits, of course. So it's 1.5 units when it's a miss. It takes a little bit longer. Okay. Now, the main memory read is much slower, 4 units. If you combine the three, according to the formula I just showed you, it gives you this delta Q. So it's kind of going up like a step up. You have 95%, it's here, and then the final 5% comes here after 5.5. So you can compute the overall delta Q of the cache. Okay, so that's nice, right? So this extra operator, this is an important operator. It means that the system will do one or the other of two actions. Okay? Okay, but it's not done yet. I will show you more examples. Here's a very important one, a timeout. Okay? So here's a timeout. So here's a block diagram. I'm sending a message to something in the cloud. Okay? And an answer is coming back. But maybe it's slow, this response, so I'm going to do timeout. So when I send the message, I will initialize a timer, and then I have this merge that will receive the timeout after the timer and the response, and it will return basically the first one, only the first one, and not the second one. Okay? So that's a timeout. If the response is too slow, then it will time out. So this is modeled using another kind of operator, which is called first to finish, or any to finish. So this is a box with an existential symbol. So when I do this one, it means that whichever of these two outcomes finishes first will be the overall outcome. That's a very kind of sophisticated thing, huh? Because these are probability functions. It turns out you can compute the delta Q of this overall thing with the two delays here and here. And this is the formula. Interesting. We will derive it in a few minutes. So delta QCT is delta QC plus delta QT minus the product. So what does this give? Let me show you what it gives. So here is the delta Q of the cloud. Okay, it takes time, and sometimes it's very slow. Here's the delta Q of the timeout. It does nothing, but at the threshold, it goes up to 1. So if you combine these, this is the final delta Q. So if you're below the timeout, it's behaving normally, but at the timeout time, it immediately jumps to 1, 100%. That means nothing ever is greater than that. You have 100% chance of getting a response up to the timeout threshold. Okay? So this is the delta Q of the timeout. Okay? So interesting, huh? Isn't that interesting? And this is the way we write it. So if you ever have a system where you do multiple things, and you're only interested in the first one, then you use this first to finish operator. Okay, interesting. So now we already have several operators here, huh? We started by sequential composition when we had pipeline. Okay? So that's an easy one. There's no special symbol for that. We added probabilistic choice for the cache, where you choose one or the other. First to finish is actually a synchronization, where you wait for the first. But actually we need one more operator, and it's called all to finish. So when we wait for both results, or all the results, we're not just waiting for the first one, we wait for all of them. So now let me show you an example with all to finish. This is, let me call it parallel work example. And this is a typical all to finish thing. So I have a task coming in here. And this task takes a lot of time. So I split it into subtasks, and I send each subtask to a separate worker. It's like parallelization, okay? And then, when both of the workers are done, the task is done. So the overall time is actually all to finish of these two. Okay, because the overall outcome, and it's written like this. So there's a prefix operator, and we have T1 and T2. So the overall outcome is done when both of them are done. So what does it give? Actually, it's the product of the two cumulative distribution functions. So here's an example. So let's say T1 is fast. It's like this. T2 is a little bit slower. So what is T? Well, if you make the product of these two, you see T2 is 0 here. Well, it's 0 here. And when T2 is here between this part, T1 is 1. So it's basically going to wait. It's a kind of maximum, but it's not actually the maximum because we have cumulative distribution functions. So the QT is actually waiting for the final one. It's also called last to finish, this operator. You can call it all to finish or last to finish because it's basically waiting for the final one. But this is a simple case when it goes from 0 to 1. These are uniform distributions, but they can always also be curves, of course, and then you have to do a real multiplication. So this is interesting, You wonder where these equations are coming from, Because they're actually correct, these equations. So let me make a detour and talk a little bit about the semantics. And it's not that hard, actually. So the idea is that if we have an outcome diagram, and we know the delta Q's of all the little pieces, we can compute the delta Q of the complete diagram, or like the complete cache of time modes. Notice delta Q is actually a function. It's a function of time, the delay t, and it represents a cumulative probability, okay? So this delta Q that we're computing is a function. It's not just a number. And I've shown you 4 operators. Sequential composition, probabilistic choice, last to finish, which is also called all to finish, first to finish, okay, which is also called any to finish. So, and these in blue is actually the computation we're doing. So we can actually make a formal language of this and give you the semantics. But I'm not going to do it like that. Let me just show you it in terms of diagrams. So the first one we saw was basically a pipeline with 2 outcomes. The end event of OA is the start event of OB. Okay, causally connected. In that case, the probability distribution is the convolution. So technically, the derivative of delta Q is the PDF, it's the probability density function, and we're actually computing the convolution of the PDFs. So the equation is this. The derivative of the result is the convolution of the 2 derivatives. These are all PDFs. And this plus symbol is a convolution. So, and very curious, convolution is actually commutative. But the system is not commutative, because OA does something and OB uses the result of A. So even though the convolution is commutative, the system is not commutative, of course. Okay, so that's that we saw. Now look at this. We're going to think in terms of probability. There's 2 possible outcomes, A and B. Exactly one is chosen during each occurrence, so starting with one of those 2 is going to happen. OA, so P and Q are the probabilities. OA occurs with this probability, OB occurs with this probability, and therefore the probability of having one or the other is going to be this weighted sum, okay? Because you have only one or the other, okay? And so that's probabilistic choice. It's a weighted sum. Let's look at all to finish now. Now we have to think a little bit more precisely. All to finish. We have 2 outcomes. So that all to finish is done when both of them are done. All to finish outcome occurs when both end events occur. But let's look at the probabilistic definition of this all to finish or last to finish. This is a cumulative probability. So if I write it, it's like this. The probability is a function of t. That dA, okay, some number that is random variable for this one is less than t, and dB is less than t. Okay, because we're both of them, we're waiting for both of them to be done. So both of them are less than t. Both of the actual values of these 2 random variables are less than or equal to t. And since the 2 events here are independent, the probability of a conjunction of 2 things that are independent is the product. So this comes from probability theory. So it's basically the product of these 2. And P, this one, probability dA is less than or equal to t, is exactly delta QA. The other one is delta QB. So the cumulative distribution is just the product of the 2. Okay? And now, first to finish, which is essentially a duo. This is very interesting. So here's the first to finish. It occurs when at least one end event occurs. At least one. But how do you compute at least one? Well, the best, because at least one could be 1, 2, 3, 4. It's at least 1. So there's not just one value. So let's compute the opposite, the negation. Let's compute the probability that there are 0 end events. So that's one thing, okay? That we can write an equation for. So the probability that there is 0 is 1 minus the probability of at least 1. Okay? So this is the probability that there is 0. It means the random variable for A is greater than t, that means it's 0. The random variable for B is greater than t, 0. Because they're independent, it's the product again. And this one is actually 1 minus delta QA. This one is 1 minus delta QB. And if you simplify this, you get this very interesting equation. Delta cube, the first to finish, is the sum minus the product. Interesting, huh? So this is a perfectly precise semantics. Okay? Okay, there's also the notion of inversion. We have the known delta Q, and we need to find a subcomponent, the required delta Q. So this is deconvolution, which I'm not going to get into because it's a complicated thing. For the other operations, there are also inverse operations. Basically, there's many possibilities. If you want to do the inverse of first to finish, there's many possibilities. Okay, so I'm not going to get into that, but a software tool would have to worry about that. Okay, let me now show you a more complicated example, which is this one. This is a realistic example. It's a networked memory with a local cache and a timeout. So here I have a local computer. It does a read, it goes to a cache. If there's a hit, it comes back. If there's a miss, it goes to the network, and the main memory is on the other side of the network. So eventually it does a main memory read, return, comes back. But the main memory read can time out. So there's a timeout here. Okay. So it might time out. So this is the outcome diagram. So we have the read event here. So hit or miss. If it's a hit, we're done. Okay. If it's a miss, we come here. There's a miss. But the miss, it means we start the main memory read, but we have to do timeout. So the timeout means that there's a first to finish for the timeout. So we do first to finish. If the timeout finishes first, we're done. But if it doesn't, we do the network. So this net is the actual delay of the network. We do a main memory read. And notice I'm also modeling the fact that the main memory can fail. So the main memory has an error correcting code, and it has 10 to the minus 16 chance of failing this error correcting code because of cosmic rays and whatever. So there's even a probabilistic choice there. So you can actually even model that, okay? Otherwise you would just have a perfect main memory. So this one is even modeling the possibility that the main memory can fail. And when it returns, it goes back to the network, and then it returns. So this models exactly the causal behavior of that. So this is an interesting representation, you agree? And if you know the basic delta Qs here, you can derive the performance of the whole system. What do you think of that? Interesting, huh? And this is new. This is something that people didn't really know. Or that people knew, but nothing was written down. So you guys are some of the first ones. PNSol knows this. Okay. Now delta Qs happen all the time in the world. I showed you idealized ones. Let's see what happens with real world things now. Typical delta Qs. Okay? I'll make two parts. So first of all, we want to do some back of the envelope. So I'm going to use two delta Qs, Gaussian distribution and uniform. So we already did uniform, right? And then I'll show you the delta Q for a typical component. Any random piece of software, you send it a message and get a reply, it will have a delta Q. It's pretty close to what we showed here. Okay, interesting. I'll also show you what is the typical delta Q for a real network. So this is something that is you observe and you can see for real networks. Okay, so let's first look at Gaussian and uniform. This is for back of the envelope computation. So of course, a software tool can take any curve and compute with it, huh? But it's not so easy for me as a human. So a good engineer will do back of the envelope. And there's two very important ones for that, Gaussian and uniform. Gaussian is good when you combine a lot of things, and uniform is good for single pieces. So I'll show you what that means, okay? So here is the two kind of useful ones for back of the envelope. So a Gaussian distribution, so here's the CDF of a Gaussian. So this approximates the sum of many independent random quantities. This is a famous theorem called central limit theorem, which you all know, of course, right? So we use that here. So this is very important. It means this is a very good approximation for when you combine many independent things. But not for single things. So it's not good for everything, okay? But it's good for that. But uniform is good for one thing that you're looking at. So a component in the system, a single will have a behavior very similar to this. Not exactly yet. There is some variation, but it's close to this. There will be some minimum time, so before little a, 0, and after little a plus SA, you're 100% sure it's done. Okay? So the work is done in this time period. So that's important. Whereas a Gaussian has infinite tail. This number, this thing goes on forever and never actually reaches 1. But this actually reaches 1 here. Okay? So this is good for single parts, but not if you connect a lot of parts. Whereas this one is good for connected parts, but not for single parts. So they're kind of complementary. Okay? So I show you some formulas for this. So this is very standard, huh? So if I do convolution of two Gaussians, I get another Gaussian, and the mean is the sum of the means, and the squares of the standard deviation is the sum of the squares of the standard deviation. So that's a standard result. In probability theory, you can do approximate result for uniform. For uniform, it's not exact anymore, okay? But it's good for back of the envelope. So if I connect two uniforms, the result is almost uniform. Now, if you connect lots of uniforms, it'll turn into a Gaussian, okay? But if you connect two uniforms, it's still kind of a uniform. Here you can see the difference between the exact in red and the uniform approximation. So this is the formula I used before. So the difference between this exact and the 0 is actually quite small here. Right? It's only a few percent, so here and here. So, and here it slightly extends beyond the straight line. So it's still a pretty good approximation. Okay? So the lowest value is the sum of the low values plus a little bit more. The high value is the sum of the high values, a little bit less. And the spread is the maximum of the two, a little bit more. So it's a little bit worse than just the combining. Okay? So that's the uniform. So this is an approximation. Okay. And now I want to talk, so that was just back in the envelope. Now I want to talk to real components, real things. And there's two things that you see in systems. You see boxes, components, like databases or browsers, whatever, and networks. Those are the two things, components and networks. So the delta Q's of those two are I'm going to show you them. So let me show you first. This is now coming from queuing theory. Queuing theory is a classical discipline which computes stochastics of systems where you have people waiting in line in the store, for example, queues and services. Has anyone here, do you have seen queuing theory? Anything at all? No queuing? You have seen it? Mm-hmm. Where? In what course? In
performance architecture.
Oh, who's teaching this one?
Tom Barbette.
Tom Barbette shows you queuing theory. Mm-hmm. Oh, that's good. I'm very pleased. Okay. So this is a small part of queuing theory. So we're going to model a component with a particular kind of queue. Okay. So and there's 4 parameters here. So this typical queue, there's messages coming in and messages coming out. And each message in, there's a message out. Now the incoming messages have an arrival rate, certain number of messages per second. So that's a queuing parameter. But there's also a service rate. how fast can this queue treat the messages? There's a little server in there that does the work. So the load of the queue is the ratio between the arrival and the service. So if this guy can service 100 messages per second, and I send 100 messages in, then the load is 1. Okay? The offered load is 1. It means I'm matching the internal load. Whereas if I send only 50 messages in, the offered load will be 0.5. Okay? So 1 is actually kind of the cutoff point where the load is low or high. And also there's going to be a buffer inside. So the buffer size is a number, a constant k. So those are parameters that you can tweak. K, it's harder because it's part of the construction of the queue. But the offer load can vary in function of time. And then there's the output of this. So this guy has a delta Q, of course. But we can model delta Q in queue theory by two numbers, a failure rate and a delay. So the delay and the failure rate, so this could either be an average or it can be a distribution, okay? And there's a failure rate. So the delta Q will be a function of the load and the buffer size. That means if you increase the load, the delay is going to increase, okay? That's very reasonable. If I have very low load, I'm only sending very slowly messages. Each one of them is by itself. The queue is going to have the same performance. But if I send many messages, then they will be queuing up inside, and especially since they're not uniform per time, and that means the delay will increase. Okay? So this is how the queue is modeled. So this is technically known as an MM1K queue. So there's many different variations. So each of these symbols has a meaning. The first M means arriving messages are exponentially distributed. That means they're independent, basically. The rate is constant, but the times between them are independent. And there's no memory. Also, there's a little computer inside the components doing the work. And it takes time to do the work. So the service time, but this time varies also. This is also exponentially distributed. Some things are easy, some things are hard. But there's some average service rate, okay? So both of these are MM. So why an M if it's exponential? Because M stands for memory less. Okay, there's no memory. Also, one message can be served at a time. This server can only do one thing at a time. And the total buffer size is K. I mean, there's 1 here and K minus 1 here. So the offered load is the arrival rate, which is usually written lambda, the number of messages per second on average, divided by the service rate, the number of messages can be served. So these are the two knobs we control, the load and the buffer size. Notice when the buffer is full, new arrivals are dropped. So this queue has failure. If the whole buffer is full and a new message arrives, that message disappears. Okay? So there is a failure rate in this queue. This models actually quite well how components work. So the offered load is a very important parameter. Okay? If the load is less than 1, so every component has its maximum, has its capacity. And if it's less than 1, then we're good, it has enough power. But if it's greater than 1, it's overloaded, and very bad things happen. But 1 is not exactly the number. It's less than that. If it's less than 0.8, things are okay. But if it's actually very close to 1, it already starts doing bad things. Okay? So high load, I would define as something like this. If it's 0. The problem is the messages are not uniform in space. Some of them are bunched together. So that even if the load is less than 1, we can have problems. Okay? When A gets close to 1, things get worse. When A is bigger than 1, things get very bad. You're giving this component, let's say, 10 times as much tasks as what it can do if the A is equal to 10. So what does it do? Well, it does 10% of them, and 90% of them it just throws in the garbage, okay? So the failure rate is very high. So overloading is a very nasty thing. The delay is very quickly increasing when the load approaches 1. See, this is a very good intuition when you're building systems now, this load. And there's some transition that happens between 0.5 and 1. When the load goes beyond 0.5, it gets pretty bad, okay? And notice here in blue, even temporarily, if the load for a very short time, a few seconds, it goes very high, 10. What happens? It causes a huge degradation in performance, which is long-lasting. Why is it long-lasting? Because it fills the buffer. And the bigger the buffer is, the worse it gets. Okay? So this is the cause of the problem in the small cells study, yeah? So here you can make kind of a diagram. This is very approximate. Huh? I'm approximating using uniform. So very small load, then you have something like this, and this number is basically very small, and the service time is S, and the failure rate is basically 0. So very good, low, very nice. If it's very high, then you have very, very bad. You have huge delay, huge delay. This is the size of the buffer, basically. And then you do it, and then the failure rate gets very, very big. The more, this lower this value gets, okay, it gets very bad. And when A is equal to 1, it's kind of in the middle. It actually fluctuates a lot. The average delay is going to be half the buffer size, but it's actually fluctuating a lot, which maybe you don't see in this diagram. So the buffer size, that's the other parameter. The load was the one thing. Buffer size. Now we get to something very interesting. When you buy a component, let's say you buy what's called a NIC, a network interface card, that connects to the computer, this network, and it has buffer in there. The manufacturer says, my buffer is the size 1,000, huge. The other one says, my buffer is better, 2,000. It might seem like a no-brainer that bigger buffers are better. It's completely wrong. These big buffers are very bad, actually. Okay? Okay, there's two cases, low load and high load. In very low load, then big buffer is okay. But you don't really need a big buffer in low load, because it's never going to be full, okay? But still, they will somewhat, a little bit to decrease the failure. But since the load is low, they actually never fill up, so you don't really need a big buffer. Okay? But it's not bad. But at high load, the big buffers are extremely bad. Okay? It greatly increases the delay. So let's say you have a NIC that stores 1,000 packets in the buffer. When you have a temporary overload, the buffer fills up. It has 1,000 packets. And now, how do you empty that buffer? Very slowly. One packet at a time is going to go out at the rate of the service time. So that delay of the server is multiplied by 1,000. Okay? So with temporary overload, the buffer will fill quickly and empty slowly. This is very bad. So big buffers are actually not good. Okay? Don't buy a system with big buffer. Okay? So that's a conclusion. So here's another example of an outcome diagram. This is load balancing, which is another thing people do. Here we have a task coming in, and it either goes up or down. So we're kind of balancing. We're doing part of the work here and part of the work there. So this is a probabilistic choice. We have part of the work is here, part of the work is in these two different outcomes. Okay, it's modeled probabilistic choice. And the load A, now let's compute what happens with the load. So there's a load A here, and here we have P times A, which is less than A, and here we have Q times A. And so the delta Q here is delta Q, which is a function of load, PA. Here it's a function of QA, and this one is a function of the load. Okay? So we have this equation here. Notice this is not, you have this A here. These are all functions of A. Now, if you want good performance, these servers should not be overloaded. That means the loads for 1 and 2 should be less than 0.8. Okay? And if we have the P and Q is equal to 1/2, that means the total load coming in here should be less than 1.6, which is the sum of these two. Say 1.6. So you can see you can actually get higher load, of course, if you split the load here and balance it between those two. Okay? So you can see, modeling this kind of system, you can be very precise on what happens with low and high loads. Okay? If you increase the load then things will get much worse, okay, as we saw. Okay, let me do one more thing. Delta Q for a network. So networks are not the same as components. Networks are funny beasts. Okay? So here's network packets. What is the real delta Q we see in the real world when we send a packet into this cable and routing or whatever, traveling thousands of kilometers and eventually coming out there? Experience shows that this delta Q has 3 parameters, which I call G, S, and V. And they have to be added using convolution. Okay, so let's investigate that. So there's 3 sources of delay here. Okay? 3 sources of delay. Okay, so here, let's start here. We send messages from A to B. Each of these little crosses is a message. So this is the time the system is running, and for each packet, this is the observed delay. So as the system runs, you see there's all kinds of fluctuations. The packet delay is not a constant, okay? So how do we study this? Okay, so let's study it. First of all, packets can have different size. In protocols, packets are different size. Here, what is the actual data transmitted in a packet? Let's sort the delay by the size. Of course, bigger packets are going to take longer. So we start to see some logic there. Smaller packets are shorter, but it doesn't go to 0. But there's still some fluctuation here. Even for packets with the same payload, it's still the same. Okay. Okay. So there's a minimum, a boundary line. Okay. This network has buffers, whatever it has around it. It has things there. So the lowest time is this green line, and this is the transit time of a hypothetical 0th packet. Okay, but it can be higher, of course. Huh? So that's already a source of time. Okay. So this minimum time is called the given delay. This is because of distance, structure delay, speed of light, routing, lookup, constant overheads. So this is the geographic delay. It's the first source. Then we have the serialization delay. This depends on the size of the packet. Okay. This is also an increasing function of the packet size. And finally, we have the variable contention delay. Okay? So this is due to various things like contention. Okay? So this gives us three sources of delay. There's also the loss, but I'm not going to talk about packet loss here. We're looking at packets that make it through. So we have the given delay, the size delay, and the variable delay. So the total delay is the sum of the 3 parts: the geographic, the size delay, and the variable function of contention and noise. Okay? There's also some lost packets, okay, which I modeled here. You could also model for delta Q. So we have these different parts. So the final behavior of the network is like this. Okay. Notice it's a function of the packet size. This delta Q is a function of S. So you see. So when we make our outcome diagrams, we will have these delta Qs of the network depending on packet size, the function of S. Okay? So then it depends on what is S. Is it constant? Is there a variation? Whatever. But at least we have this formula for the delta Q. Okay? And when we make our outcome diagram, this gives us equations to solve. Okay, so now we can go back to Cardano Shelley, but I fear we don't have time for that. So the Cardano Shelley, let me just very briefly explain what it's doing, and then we'll go into it next week. So now we know enough to design this algorithm, because it's going to be a big, complicated outcome diagram. No? So this is part of blockchain. So blockchain is a distributed ledger. So a ledger is a book where you write down financial transactions. It used to be an actual book where people wrote down with ink, but now it's a software thing. Okay? So it's a chain of blocks, and each block is a witness to the correctness of the preceding block. So they're cryptographically connected together. So the sequence of blocks, which are the transactions, has to be globally agreed on by everybody. So you need a consensus algorithm, but a very interesting kind of consensus, because a consensus that works even if you have adversaries, people trying to cheat, Byzantine consensus using cryptographic techniques. And so the Cardano blockchain uses an algorithm that they invented called Ouroboros Prowess. Okay? And it uses what's called distribution of state to select a node to produce a new block in some time interval. Okay, so this is where our algorithm comes in. So we choose some node to produce the block, and this node needs a copy of the most recent block. So the most recent block has to be kind of copied to all potential block producing nodes, kind of a broadcast. This is called block diffusion. So we're going to design block diffusion. So this is a part of this, the blockchain, the distributed blockchain algorithm. So here's the idea. We have a bunch of nodes. They're connected in some random, weird way, okay? We pick two randomly chosen nodes, A and Z, okay? And the block diffusion is going to eventually diffuse. So we need to design an algorithm that there is a well-defined delay between A and Z, randomly chosen, okay? And the basic input is that the delay between any two nodes, X and Y, is a known delta Q X, Y. So we have to design an algorithm that where the QAZ defines has some constraints. And there's some parameters here. The frequency, the node connection graph, the block size, the forwarding protocol, processing time. So there's lots of parameters. Okay? So all of that goes into our outcome diagram. Okay? So we want to design a good algorithm and prove that it's going to be fast with all this variability and randomness in there. So we need something like ΔQSD to do that. Okay? So we will do that next week. Thank you.